this section, we will be looking at verifying trig identities. This is section 7.2 in our book. So, yesterday we learned several trig identities. Those you should be working on memorizing, and we're going to put those to work here. In verifying trig identities, you must simplify in order to show that both sides of the equation of the equal sign are the same. You may not move anything from one side to the other. In solving equations, we might add 2 to both sides. We cannot do that here. We have to work on each side separately. So let me show you an example. So we have sine to the third x plus sine x cosine squared x equals sine x. So what we're going to do here is we need to simplify so that both sides of the equal sign are equivalent. Now, obviously, on this problem, we need to work on the left-hand side here because this is much more complicated. There's not much we can do to sine of x. So we have sine cubed x plus sine x cosine squared x. One thing I notice here is that I've got 3 sine x's here. I've got 1 here. So this is kind of like having x to the third plus xy squared. And if I have that, I could factor out an x. So if we kind of do this side example to remember to factor out that x, I would divide both of these by x, write that out front, and that would be x squared plus y squared that I would be left with on the inside. So similarly here, we're going to factor out a sine x. So I'm going to factor out a sine x. That will leave a sine squared x, and then in the second term we'll have cosine squared x. So you can see now that there should be an identity that is popping out to you right here. Sine squared x plus cosine squared x is our Pythagorean identity. So we can replace that with 1. You have to show that step when you're verifying, because when you're verifying identities, when you're verifying identities, you already know the answer. The answer is that this side equals sine x. So I'm not interested in whether or not you get the right answer. I'm interested in that you show the work to prove that that is in fact the identity. So we need to write sine x times 1 here. Now everybody knows sine x times 1 is sine x. But we have to write this step because that lets me know that you knew you could replace sine squared x plus cosine squared x with 1. And then our last step is that we would just have sine of x here. Now both sides of the equation equal sine x. So we have verified this identity. We have proven that it is true. Now the difficult part about verifying identities is there is not a set way to solve every problem. Every problem might warrant a different approach. So we don't always factor out a sine x like we did here. Sometimes we might do things that are totally different. So this slide here gives you a few strategies that are good to try. As in the last problem, I transformed the most complicated side first. That would usually be the best approach. Substitute basic trig identities to simplify, things like sine squared plus cosine squared equals 1 that we know. Sometimes you might need to factor. In the last problem I did, I factored out a sine x. But other times you might have something where it might be helpful to multiply things back together rather than factoring. So we will see some problems that have fractions in them. We'll have to get like denominators and add those together. One good strategy to use whenever you have tangent and cosecant and secant and all of those things in there, it's a good idea to change everything to sine and cosine and then work from that. So those are all strategies that we're going to try. So here is another example. We have cotangent theta equals cosecant theta over secant theta. So I can see here, there's not really anything I can do with these as they are. But over here for cosecant theta and secant theta, that side is slightly more complicated. And I could change everything to sine and cosine. We know that cosecant theta is 1 over sine theta. And we know that secant theta is 1 over cosine theta. So now what we have here is a complex fraction. We don't like to have complex fractions, so we are going to divide those fractions. It's easy as pie. We are going to flip the second and multiply. So whenever we do that and multiply, we get cosine theta over sine theta. And cosine theta over sine theta is cotangent of theta. So now I see that I have both sides are equal here. So I know I have verified that identity. Now, it's a possibility that you can work on both sides if you want. To give you an example here, let's say on this problem that I just did, let's say that on the right-hand side, I stop here at cosine theta over sine theta. So for cotangent theta, I could say cotangent theta is cosine theta over sine theta, which is also true. So that shows that that identity is true. As long as the bottom line of both sides of your equation are equal to each other, you have proven the identity if your work to get there is correct. Okay. For our next example, we've got secant squared theta minus tangent theta cotangent theta equals tangent squared theta. So for this problem, an approach most students will usually take is to change everything to sine and cosine just like we did before. So we would have 1 over cosine squared theta minus sine theta over cosine theta times cosine theta over sine theta. So if you notice here, whenever you change this, the sines here will cancel and the cosines here will cancel. So what we'll be left with is 1 over cosine squared theta minus 1. So what we're dealing with here doesn't look anything like tangent squared theta. But we could get common denominators. So if we get common denominators, that means this second term here needs to have a cosine squared theta in the denominator, which means we must also multiply by cosine squared theta in the numerator. So we have 1 minus cosine squared theta over cosine squared theta. Now, this looks nothing like tangent squared theta, but there is an identity that we can see here. Now, it's not an identity that's really easy to pick out at first, but this 1 minus cosine squared theta is an identity. It comes from our Pythagorean identity. Our Pythagorean identity, it's usually the only one anybody remembers, sine squared x plus cosine squared x equals 1. Well, watch what would happen if I subtracted cosine squared x from both sides of that identity. I would have sine squared x equals 1 minus cosine squared x. So you can see here that 1 minus cosine squared of a variable equals sine squared of that variable. So we can replace 1 minus cosine squared theta with the sine squared theta over cosine squared theta. And sine over cosine is tangent, so we get tangent squared theta here, which is, of course, what we were looking for so that it will match the other side. Okay, our next example looks really difficult, but it's not as bad as it may originally seem. We're going to use a strategy here that maybe I should have listed on the strategies earlier. And this is a strategy that is not as this name, I'm going to give it quite a sound mathematical term, but we're going to do the love connection on the left-hand side. That means we're going to divide the first term by sine x cosine x, and we're also going to divide the second term by sine x cosine x. And I call this the love connection because if you circle it like this, you got this cute little heart here. So we're dividing both terms by that denominator. So we're going to have 7 sine x over sine x cosine x plus 5 cosine x over sine x cosine x. And notice here, conveniently, our sine x's cancel here, our cosine x's cancel here. So that gives me 7 over cosine x plus 5 over sine x. Well, 7 over cosine x, since cosine x is in the denominator, this is the same as 7 secant x. And 5 over sine x is the same as 5 cosecant x, which of course is what we wanted from the other side. Like so. So that gives us the correct answer on that one. Now, one important thing to remember whenever you're doing trig identities is there's not one set way that you have to do every problem for most of these. So I'm going to redo number 4 in a different way. I'll erase what I have here. Instead of working on the left-hand side, I'm going to work on the right-hand side this time. So what I'm going to do is I'm going to change this to 7 over cosine of x plus 5 over sine x. Now, I could get common denominators to put these together. So that means I would need to multiply this by sine x on top and bottom. I would need to multiply the second term by cosine x on top and bottom. So that would give me 7 sine x plus 5 cosine x all over sine x cosine x. And if you notice, that of course is what we have over here on the other side. So that proves this identity. Now, this isn't very pretty. It's not simplified at all. It looks worse than what it did when it started. But both sides match, so we've proven this identity to be true. Okay? And here is our last problem. So in this one we have sine of a over cosecant of a plus cosine of a over secant of a. So my strategy here is going to be to change everything to sine and cosine. So I'm going to have sine of a over 1 over sine a plus cosine a over 1 over cosine a. And I like to put parentheses around those denominators so that I don't get mixed up with all those lines for the fractions. Dividing fractions is easy as pie. We're going to flip the second and multiply. So I'm going to have sine of a times sine a over 1 plus cosine of a times cosine of a over 1. So now, sine a times sine a is sine squared a. And of course over 1, but we don't have to write that. Cosine a times cosine a is cosine squared a. Now, here's our Pythagorean identity. We know sine squared a plus cosine squared a always equals 1. So for this, we get 1 equals 1, and we have proven our identity.